I think this video is going to explain it pretty well. I have a couple of example problems I'm going to work through, and then I have a couple for you guys to try on your own, and the answers are in the video just to make sure that you kind of understand what's happening. You will have bookwork to do on this on Monday, so please bring your textbooks on Monday. It's looking like your test over fluids will be on Friday of next week, so when I get back to class on Wednesday, we will do some practice tests and go over your FRQs and all of that. This video should give you guys enough information that you can start working on those FRQs that I didn't star. So after you watch this, it might be worth the time to take a look at a couple of those because they have to do with what we're going to talk about here now. So far with our chapter in fluids, we have talked about fluids that aren't moving. We've discussed things like buoyancy and pressure, but now we're going to start looking at what happens when fluids start to flow, and that's called fluid dynamics. For all of this dynamic work, we're going to just be dealing with what's called ideal fluids. And for a fluid to be ideal, it has to meet three criteria. The first criteria is that it's non-viscous. That means that there's no internal friction happening with the fluid at all. Most of the time, we're just dealing with water. Every once in a while, we're going to do a problem with air flow, but most of the time it's water. The fluid has a constant density, and the fluid is in motion, and it's non-turbulent. So let's have a quick discussion about what that means. There's two kinds of fluid flow. There's turbulent and laminar. And for all of our purposes, we're looking at laminar flow. A laminar flow is very streamlined, very smooth, no bumps, no weird swirls. When the fluid doesn't have laminar flow, it has what's called turbulent flow. And this is where you get things like eddy currents happening. And here's a little graphic to show you guys the difference between turbulent and laminar. But everything we're going to do is laminar. So no need to worry about that. Okay, the first thing we need to discuss is the idea of flow rate. This is called volume flow rate. For ideal fluids, the following fluid flow continuity equation applies. The area of the opening times the speed of the liquid through the opening is constant throughout the pipe. So that means that if the area decreases in a pipe, the water speed has to increase. Conversely, if the area increases, the water speed has to decrease. So this value is the same everywhere along the pipe. It comes from the idea of this conservation of mass. So the amount of mass of water that we have flowing through this region here at a particular rate, that same amount of water has to get through this pipe down here. So in order for it to do that, it needs to speed up. Everybody's probably seen this concept whenever you water your lawn. The water comes out of the hose at a particular rate, but if you cover part of the hose up with your thumb, now all of a sudden the water moves much faster because you've decreased the area of the opening of that hose. And so in order to move the water through the hose at the same amount of water through the hose, it needs to speed up. All right, so here's an example of that concept using blood in the body. The speed of the blood in the aorta is 50 centimeters a second, and the radius is 1. If the capillaries have a total cross-sectional area of 3,000, what is the speed of the blood in the capillaries? So you can kind of look at, of course, your body as one just big pipe for blood. So the area of the first region times the speed in that first region equals the area in the second region times the speed in the second region. So we have a pi r squared for the area of the circle. And then for the first... for the aorta, we have pi times r squared, which is 1, times 50, which is the velocity, equals the area of your capillaries, which is 3,000, times the speed through the capillaries, and you get 0.052 centimeters per second. All right, Bernoulli's principle. This is the real meat and potatoes of what we're going to talk about today. Bernoulli was a Swiss physicist, and he was really interested in trying to relate the idea of pressure to fluid flow. And what he discovered was that as the velocity of a fluid increases, the pressure in that fluid will decrease. So a change in pressure results in a net force towards the low pressure region. Here is a graphic that kind of explains that. As the speed here is increasing, you have a decreasing pressure. This is kind of the idea behind how airplanes get off the ground. We have the wing of an airplane here, And the top part of the wing is very aerodynamic, and it allows the air to flow over it faster than the bottom part of the wing does. So the air moving on top of the wing is moving at a higher velocity, which means that the pressure on the top of the wing is less than the pressure that's on the bottom of the wing. And so the airplane experiences a net pressure or a net force upward, and it helps to provide that lift so the airplane can get off the ground. You can also see Bernoulli's principle and a couple of examples you could do at home, I guess, if you wanted to. This graphic over here is actually a little bit creepy, but it gets the idea across. These are two pieces of paper, and sorry about that. And if you hold them kind of close to one another and blow in between them, what you're doing is you're increasing the velocity of the air here in between those two pieces of paper, and it's going to create an area of lower pressure. And so the higher pressure on the other side of the paper is going to push those pieces of paper together. And you can also do this with empty Coke cans. If you put them on the table kind of close to one another, take a straw and blow through them really quickly. Just leave a little bit of space in between them. It's like they're almost magnetized to one another, and they'll fly together. This is an example of the same thing with ping pong balls. TIA, this is an example of Bernoulli's principle happening in your body. And if you guys watched the Texans game last week, you heard that Gary Kubiak suffered a trans-ischemic attack, which is what this TIA is. And the idea behind it is Bernoulli's principle. So here's a little graphic to show you guys what's happening in the body. TIA happens, or mini stroke, happens because you have a constriction in one of your arteries. And in this picture, it's right here. So that constriction is going to cause the area in that artery to decrease, which we just learned if you decrease the area, the speed has to increase. So the blood is going to go faster through this region. But we just also learned that faster moving fluids produce a lower pressure. So as the blood is trying to come up here to the brain, it speeds up, the pressure decreases, and instead of going up to the brain over here on the right vertebral artery here, first of all, let's imagine this side of the body is the bad side and this side of the body is the good side. So on the bad side, we have lower pressure and we have a higher flow of blood. Well, your body wants to regulate the pressure so that it's the same everywhere, and in order to compensate for this lower pressure on this side of the body, your blood over here on this side is going to want to flow down over here and try to rush in and compensate for some of the missing blood pressure on this side. So that means that there's no blood making it to the brain because the pressure is far too low. And then that's when you suffer a mini stroke, or TIA. All right, so in equation form, this is Bernoulli's principle, and it's ideally just a conservation of energy expression. But we have the pressure plus the kinetic energy in terms of density plus the potential energy in terms of density. If you add all three of those up together, you're going to get the same value anywhere along the streamline of fluid. So let's do a couple of examples. I'll give you guys a second to look this one over, and then we will work it through. It's basically saying that you're going to pump water at a particular speed through a pipe, and then we want to know the pressure and the speed of the water in a pipe on the second story. So pause it if you need to write down all the variables and read through the problem. Okay, the first step in doing this is to find the velocity in the pipe at the second location. So we have our A1V1 equals A2V2. So the area times the speed at the first location equals area times the speed at the second. Here is the area of our first. Oh, I forgot to put the pi in there. Sorry, guys. You should have a pi right here. And then the area, well, I guess it's going to cancel out anyways. Area in the second region over here. And then we have our velocity at the second point ends up being 1.183. So now the next step is finding the pressure at the second location. And Bernoulli says that P1, pressure at the first location, plus kinetic energy plus potential energy at the first location, equals the pressure plus kinetic plus potential at the second. So this is our expression. We're going to assume that the first location, we're going to say that that's our 0 point. I know it was in the basement and it's below ground, but we're going to count that as our 0 point. And this ends up being our expression. This is our pressure at the first point, kinetic energy at the first point. Pressure at the second point is unknown. We know our kinetic energy and our potential energy at the second point. And we end up with 2.5 times 10 to the 5th pascals, or 2.5 atmospheres. Okay, here's another example. Go ahead and pause this one and write it down, and try to do this one on your own before you see my solution on the next slide. But we need to find our flow rate just like we did in the previous example. We need to find our velocity of the water at the second point, and then the pressure at the second point in the pipe. All right, so here is our answers to part A and B. The first part wants to find the volume flow rate, and it's 0.014 because all we did was multiplied our area at the first point times the velocity at the first point. Now that has to equal that at the second, so for part B, finding the speed at the second point is going to be 7.2 meters per second. Here is the part C, finding the pressure at point 2. So we have this expression again for Bernoulli's principle. And in this case, there's no change in height of the pipe, so everything is on the same level. So your potential energy expression here can just cancel out, and we're left with this. And then when we plug our values in, you should have gotten 7.54 times 10 to the 4th Newton meters squared. Okay, this is actually example 3. I don't have the solution for this one. I do have the answers on the next slide, so if you want to pause it and try to work this one out on your own, I will show you guys the solution on the next slide. And there it is, and hopefully you guys got that right. And if you have any questions, please feel free to email me. You guys will have bookwork over this concept, so please bring your textbooks on Monday. Thanks, see you guys later.